Hello, welcome back. So it's my pleasure to introduce Aline Andrade, and she'll talk about rank 3 instanton bundles on the projective 3 space. Please, Aline, go ahead.
Thank you so much. First, I would like to thank you, Marcos and Amar. Thank you so much for the invitation. It's very nice to be able to talk in this kind of event. Well, I forgot to put here, but I'm from Universidade Federal Fluminense. I will add this later. Well, today I will talk about instanton bundles. I will talk a little bit on rank 3 instanton bundles on projective space. And this is a joint work with Danilo Santiago and Luis Sobral from Unicamp and Danilo Silva from Universidade Federal do Sergipe. Okay, so why we want to talk about these instantons and try to work on this problem? Well, since the 70s, the instantons or pseudo-particle solutions of the Young-Mills equations has awakened a great interest in the physical and mathematical communities. We have works on higher dimensional projective spaces. We have works talking about symplectic instanton bundles, orthogonal instanton bundles, special instanton bundles. And this is so, it's a little bit of all of can be done and be studied in these bundles. Well, the instanton bundles of rank 2 on P3, with second Chern class equals to n, so we fix the second Chern class. They fulfill a reducible component of the modular space of vector bundles. So it's natural for us to ask what happens when we go to the higher ranks instanton bundles, okay? So we will start with rank 3. But first of all, I will introduce some preliminaries. The first preliminary is interested that I talk about instantons and start with preliminaries of Hartrann-Serre correspondence. But this will be a very good tool, a great tool for us to study these bundles. So this is a generalization of Hartrann-Serre correspondence made by Arrondo, and it says the following. Let X be a smooth algebraic variety, and if be a codimension to locally complete intersection subscheme. So we took the normal bundle and a line bundle in X such that this vanishing occurs. So we assume that this is generated by R minus 1 global sections, where R is the, let me see over here. And then we have the following. There exists a rank R vector bundle, so it depends on this amount of global sections over here. And then we have that this line bundle is this wedge, and that F has R minus 1 global section, which depends on the locks of this guy. And we also have this here. So this last condition is just will not be important for us now. Okay. Well, I don't know if you can hear me well because my neighbor is make some noises in here. But let's continue. If you not listen me well, please raise your hand. Okay. Well, we'll use this correspondence to talk about instantons. So let's remind what an instanton shift is. So I will use the definition of instanton shift from P3. So I will consider just these vanishing conditions over here. Okay. When we are in the general case, we have more vanishings to deal with. and the first chain class is 0. So the second chain class is that we call the charge of our instanton. And in the case that this instanton sheaf is locally free, we are dealing with instanton bundle. Okay? Well, the first result that we have is the following. We will consider a node-generated locally complete intersection rational curve on P3 of degree n plus 3 for any greater or equals to. Then this guy is generated by 2 global sections, and this bundle over here is a rank 3 vector bundle and is a instant bundle of charge n. So this is just a sketch of the proof. So we will use this result of Jardim, Markusevich, and Tikhonov to show that this guy is in fact this piece over here. So we can make some computations and prove that this is generated by 2 global sections. So we can apply the Hartree correspondence, and then we have this exact sequence over here. And this bundle in here is the corresponding rank 3 bundle given by the Hartree correspondence. So to finish the proof, we just need to prove that this is in fact an instanton bundle, but it's just to check these vanity conditions over here. So it's a good job to do. It's very easy and clean. So we associated rational locally complete intersection curves with fixed degree, with instanton bundles with this charge, which depends on the degree of the curve. So this is a very nice tool because we can play with instantons and we can play with curves. Well, our goal is to do in the other way around. Here are 2 curves and associate with the instanton. Now I want to do the converse. 2 instantons and associate with these curves. So I have a kind of bijection. Okay. So to do this, we will consider the concept of spectra. Okay. Well, to give the definition of spectra, I will need this theorem. Okay. So let F be a rank R torsion free sheaf on P3 with generic splitting type given by this. And as a global section. So exists a list of n integers over here with this order such that we can associate these cohomologies, the dimension of these cohomologies over here with this number, okay? So S is the dimension of these global sections over here. And we have this relation with this case, which appears with this number and this twisted over here, okay? Well, these numbers, in this case, are what we call the spectrum of the sheaf. And we can prove that this number and the amount of integers that appear is in fact the second chain class of our sheaf, okay? There's a lot of good properties for these guys, and they help a lot for us to try to classify bundles, to study the modular space, to study components of the modular space. So this is a very good tool, okay? So how will we use this tool? First, given a semi-stable rank 3 vector bundle on P3, and let n be its second chain class, then F, this bundle, is an instanton bundle if and only if this is the spectrum. So the spectrum, we have n integers over here, but all these integers is equal to 0, okay? The proof is very easy. So we took a rank R semi-stable vector bundle of charge n on P3 and let Kf this spectrum, which existence is given by the previous theorem. So if F is an instanton bundle of charge n, we have this vanish, which implies that the dimension of this twisted is given by this guy, which is also equals to this guy. And then we have that all the KIs must have less or equal 0. We also have that the sum of these guys must be 0. So we have, since the spectra must obey this order, that all they are equals to 0, okay? And on the other hand, if we have a semi-stable bundle with this kind of spectra, it's easy to compute these cohomologies and prove that F is in fact an instanton. So we know now that when we are dealing with rank R semi-stable vector bundles on P3 with fixed chain class, then we know when to characterize the instantons using the spectra, okay? Wow. So what we want to do next, since we have the relation between curves with bundles and with instanton bundles, we want to do the other way around. It's nice for us to achieve some relations or dependence between the invariance of the curve and the invariance of our bundles. So this theorem over here do that. We relate the degree and the genus of the curve with the, let F be a rank 3 vector bundle P3 with fixed chain classes C1, C2, C3. And let F be a rank 3 vector bundle P3 with fixed chain classes C1, C2, C3. And let Y be its corresponding curve, such that Y has degree D and arithmetic genus G. Then the degree of the curve is the second chain class, and we have this equality over here, okay? This result is due to Vogel, but we also made a proof this on our paper. We have a mistake over here. I forgot to put the number of the theorem, sorry. So this will be very useful for us, okay? So we can relate the invariance of the curve with the invariance of our bundle. So now we have the other way. So we now consider a rank 3 instanton bundle also on charge n without double sessions, and suppose that we have this over here. So it's generated for more than 2 factors. Then we have that this guy over here, which will be the normalized bundle. It's in this extension, and that Y is a rational curve, which is associated with our guy by the Hartrann-Seher correspondence. So I will not get into much details over here, but it's interesting to see that now we have the other way. So we can take a rank 3 instanton bundle and associate with a rational curve at degree n plus 3, and in the fact prove that this is a locally complete intersection, and we can also do the other way, took a rational, locally complete intersection curve, and associate with a rank 3 instanton bundle. And we are doing this only fix the charge of the instanton bundle, which depends of the degree of the curve. Okay. Well, we want to use this correspondence to study the moduli space of vector bundles. Remember that in the beginning, I say that we want to see if these instanton bundles are irreducible components of this moduli space. Okay. Well, in the Hartrand-Serre correspondence, we have that the global sections must be generated by a amount of a certain number. Okay. Well, when we are dealing with rank 3, r minus 1 r equals to 2. So we are going to use this special kind of instantons which appear natural for in this context, which are the toothed bundles. So we have this bound for the number of sections of this normalized bundle over here. Okay, so let me rephrase what I already said because I also confuse myself. We want to use this special kind of bundles because we can provide they have a bound for the number of global sections over this normalized bundle. Okay, so these special kind of instantons are the toothed bundles, and we can do this. This curve is a rational smooth curve of degree n plus 3, and F is corresponding rank 3 instanton bundle of charge n, given by the Serre correspondence, Hartrand-Serre correspondence. Okay, so when we are dealing with rank 3, we know that this guy is a toothed bundle, and then we have that he fits in the shortest axis 6 over here, and then we have the following. We can prove that in these conditions, that if we have this vanish of the action of the ideal of the curve, then we have this vanish of the x2 associated with the bundle. This will be good for us in order to prove the smoothness of the component that we are studying. We also have this, the generic stable rank 3 toothed bundle of charge n is a smooth point in the moduli space of the rank 3 vector bundles of chain classes C1, C2, C3 equals to 0 and 0. Okay? How we can prove this? So we know that the generic point in this curve, in the Hilbert schema of curve, satisfies this vanish. And so it is a smooth point. Therefore, by this previous lemma, we have that the generic rank 3 toothed bundle corresponds to a rational curve of degree n plus 3, and then we have this vanish. So we use the association that we have with bundles with the curves to prove the smoothness that we want. Now, we want to use once more the Hartrand-Serre correspondence. Okay, so we'll consider a curve which satisfies the hypothesis of the Hartrand-Serre correspondence. And so given in rank 3 coherent sheaf on P3, then these two conditions are equivalent. F is a vector bundle which corresponds to this curve by the Hartrand-Serre correspondence if and only if exists E, a rank 2 reflexive sheaf, which also corresponds to this curve, by the Hartree-Serre correspondence, and F is in this extension. So we have two sheets. This one, which is in fact a vector bundle of rank 3, and a reflexive sheet of rank 2. They both are in correspondence with the same curve, but we have that the bundle is in this extension. Our first thought was to try to prove that this guy over here is also a vector bundle, but it's easy to see that we can provide examples where these do not occur. Okay. So we have rank 3 bundles and rank 2 reflexive shifts and this relation with the extension. Okay. Well, this is in the general case. We are not fixing the chain classes, just the rank. But we will consider now a particular case, which is when we fix the chain class equals to 2. Okay. So when we are with charge 2, rank 3, stable instanton bundles on P3, and sigma is a global section of its normalized bundle of this guy, we have this pair, and these pairs are in one-to-one correspondence between these pairs over here, which are of normalized rank 2 stable reflexive shifts on the 3, which are in classes -1, 3, 3, and these extensions over here. Okay, so we start with this first step for charge 2 because the charge 1 case was already studied. Okay, and also because when we are dealing with the charge 2 case of stable instanton bundles, we can relate them with these normalized stable reflexive shifts, which has this special chain classes over here, which are already studied. And also we know a lot about the curve, what they are associated by this theory. Okay, so let's go. So now we are in the position to study the family of instanton bundles of charge 2, of rank 3 stable instanton bundles of charge 2 on P3, and we will prove that this family fulfills a reducible component of this modular space of the rank 3 stable vector bundles on P3. So we will use this correspondence to prove this, that this family fulfills a reducible component on this modular space. Okay. So let's go. So let R be the modular space of stable rank 2 reflexive shifts with these chain classes, and let it be this corresponding universal bundle. Chang say to us that R is a reducible rational variate of dimension 9 and 10. Okay, so she has this great description about this modular space of reflexive shift. Now we will consider this projection onto the second coordinate. And for every class in this modular space, by the base change theorem for relative X shifts, we have this. That is, these extensions over here on this universal bundle are isomorphic to this over here, given in the projection. And then we have this. So, and this occurs for each I equals to 0, 1, 2, and 3. And by this table over here, given by chain, we have that all these guys over here, which are isomorphic to these guys over here, vanish. Okay? So now, by the local to global spectral sequence for the X shifts, we have that these guys over here, this guy over here, I'm sorry, is isomorphic to this guy over here, this guy over here. And then we have that the dimension of this X equals to 3. Okay? And also that X given by this guy over here is a reducible variety of dimension 32 that parameterizes our pairs. So now that we use this universal bundle over here to parameterize our case and associate it with these reflexive shifts, we can compute the dimension to the family that we want. So we will consider this map given by the composition of our correspondence and the projection on the first coordinate. And then we have that this map factorizes by this guy over here and more. For every E, which is an instanton bundle of charge 2 and rank 3, one has that this dimension is equal to the dimension of this global, the space of the global sections of this normalized bundle, which is a 6. Thus, this guy by constructors is a surjective open morphism of the relative dimension 6. So, which means that all the fiber has the same dimension, which is 6, which implies that we have, in fact, that the image is equal to our instant. And so we have a reducible variety of dimension 16, because we took 22 minus 6, which is the amount of these global sections that we must remove. So we have the following result. The family of stable rank 3 instanton bundles of charge 2 is reducible and has dimension 16. Okay? Well, now our next goal is to prove that this family is in fact the whole modular space. So first we have this. Every rank 3 stable vector bundle P3 of charm classes 0 to 0 is a instanton bundle. To prove this we will use the characterization. Recall a little bit. We want to prove that every rank 3 stable vector bundle P3 with these fixed charm classes over here is an instanton bundle. So we will use the characterization of instanton that I give you in the beginning of the talk. We will use the spectrum of the bundle. So let FBA rank 3 stable vector bundle P3 of charm classes 0 to 0, and the sphere, it's a spectrum. So we have second charm class 2, so we have 2 guys over here. By the properties of the spectrum, we have 2 possibilities. These properties you can find in several places, but it's not easy to compute and see that we have only these 2 possibilities over here. Okay? Well, if the first one occurs, we have our result that this bundle is an instanton bundle. So now we just want to remove this possibility over here. Okay? So we will assume that the spectrum is 1, and then we can compute this cohomology using the theorem of, which gives the definition of the spectrum. And using the Heisenberg-Riemann-Roch formula, we have this number. So we know that the dimension of this space is greater or equal to 6. So we know that there exists a loop which is greater or equal to 2, which is r minus 1. So we can use the Hartree-Fock correspondence, and we know that we have a rational quintic associated with this guy, but a rational quintic on this condition is associated with an instanton bundle, is the only possibility. So this guy could not appear. Okay. So gluing together all these, we have this. The modular space of the rank 3 stable vector bundles on P3, which are in classes 0, 2, and 0, is irreducible and generically smooth of dimension 16. So we just need to glue all these pieces together. So first we saw that the modular space is in fact the space of the instanton, because all bundle with these characteristics over here, with these conditions, no, the characteristics is a little bit off. With these conditions over here is in fact instanton bundle, and that this is a irreducible family of dimension 16. So now let's consider a instanton bundle, which is a PA generic to instanton bundle. Then this term gives us that the extension is equal to 0. So additionally, we have that the dimension of this guy is 16, which coincides with the dimension of the family of the instantons. So we have that the generic to the instanton bundles is a smooth point of that. So this is why, because it's generically smooth. The two things instantons are the generic points, and then we also know that they give this vanishing. So it's a smooth point. Okay. So this is the references. So here we have a little bit of spectra. Here we have some considerations about the Hartree-Fock correspondence. Here we have the paper of Chang, which gives the properties of the rank 2 reflexive shifts. Here we have the definition of instantons, a lot of properties. Here we have, well, and here, we have a lot of properties that we use to prove all these terms together. Okay, guys, thanks so much for your attention and your patience.
Thank you, Aline. Are there any questions?
May I ask you a question?
Sure, go ahead, Alexander.
As I understood from your construction, your modular space I2 should be unirational, because it is dominated by a rational, right?
Mm-hmm. Yes.
Okay. Mm-hmm. And I did not follow enough about the question, do there exist instanton bundles with rank 3, of course, with charge 1 or not? Maybe it is clear somehow.
Because I don't recall, because I recall that they already been studied, but I can't recall now who studied it.
I can answer that. So there are rank 3 instantons of charge 1, but they are all extensions of a no correlation bundle by the trivial bundle. So they always have sections.
I see. So they are not stable, so to say, in the usual sense, or what?
Yeah, they are not mu stable. They are just mu semi-stable.
I see.
And they are easy to classify because they are all extensions of the no correlation bundle by the trivial.
I see. Thank you.
Okay. Are there more questions? Yes, guys.
Just a little question. In your construction of E from F, can you come back to the slide? Because I missed a little part. So the E that you construct is not one that you construct from a class of the extension of the ideal of the curve with OP3, or yes?
Yes, is the one. Because we use this. Yeah, we have this. We use this. In general, we have this. But when you restrict the charge of the bundle, we have more control. So you know where the global section is. Because if I'm not mistaken, the problem that appears that when you grow the charge, we lost control about who will be the normalized in here, which will be the guy where we will appear global sections, and as well you do not have control of these training classes over here, because these training classes, it depends of the charge. If I'm not mistaken, if the charge is n, over here we have -1, n plus 1, n plus 1. So when the charge grows, which is a problem because chain studies case, but the other cases are not studied. And also because the first place where the global section appears, it grows. I believe for charge 5, the first twist is 2. So we have to consider F2. So you do not have control. So it's not easy to do in the global sense.
And so you will have a singularity of E if the extension class will vanish in some point of the curve, but F behaves well, because if you look at the extension of the ideal of the curve by OP3 to the power 2, you have always at least one of the two that at some point does not vanish. No, maybe.
I'm trying. Can you repeat? I'm trying to follow.
No, I was just asking.
I'm a little bit slow. I'm sorry.
So your E is constructed from circumcorrespondence from the curve, no? Why?
Yes. I'm trying to see if I have one of this extension. This is one of the cases. You have something like this, okay? You have this extension with the curve, with the ideal of the curve, and with your bundle.
Okay, so the rank 2 reflexive sheaf that you obtain will fit in a short exact sequence of this kind, but on the left we just have OP3.
Yes.
Okay, and so I was just asking when you find a singularity of this sheaf, is because when you localize, the extension class vanishes at some point in the curve. This is what happens. I was just.
Oh, Gaia, I don't know. I'm sorry. Okay. I can think about it, but right now I don't have an answer.
So maybe I can help again, if you don't mind. My interference is that when you have one of these curves, which is a rational curve, and you use only one section, So
Okay.
this particular twist of the ideal sheaf, or the which will give a particular twist of the dualizing sheaf of Y, it's not generated by a single section.
Okay. So you need the two of them?
Yes. Yes.
Okay.
So it's not generated by a single section. So when you do the extension, just one extension by a single copy of O, you get a reflexive sheaf. If you, but then you can use two sections to generate the omega, and then you get a bundle.
That's why F is free. Okay, perfect.
Yeah, that's why F
Thank
is
you very
free.
much. Thank you very much. Okay.
More questions?
Hi, Aline.
Hi,
So your correspondence is bijective, but I missed maybe the point about the schematic correspondence. I mean, how do you go from just a bijection to a schematic one? Maybe if you can just say something.
you mean over here?
Yeah.
Well, let me see. Well, in this case over here, in fact, in these conditions over here, I don't know how to answer this in the short way, but it's not difficult to see that when you took these guys and used the correspondence, we can easily construct these extensions, and then you can make some computations and prove that the guy is a reflexive sheaf, which also will correspond with the curve because will appear in the sequence, and you can do the opposite. There's not a tricky step in the way, it's just the computation. I don't know if I answer your question.
Yeah, I mean, in the neighborhood, in the moduli space, in the neighborhood of the first pair, how do you get a neighborhood of the second pair, more or less?
Oh, because we are, because, okay. Here we are doing the correspondence with the points, with the pairs, to in fact translate the conditions and the things on the moduli space from one case to another, we use the universal boundary. So why this is important? You have these pairs over here. You know that you have the moduli space of stable reflexive sheets, and you use to associate with the moduli space of bundles the fact that you have the universal bundle from stable reflexive sheets. So this is why this construction is important over here. So
okay, I
bundle
see.
You see, you use the projection. We do all these things to preserve, in fact, that you are using the moduli space, because in principle, these guys over here, with these guys over here, you have a family. You don't know if you have, in fact, a variety, a skin, or something like that. It's just a family that is parametrized, your problem. So this is why you really need the universal bundle over here and do these computations. This is also why when you browse the chart, the problems appears, because you don't have the moduli space for reflexive sheaths in some of the cases that you need to study. So it's very difficult to use this tool over here.
Oh, thank you.
You're welcome.
Thanks, Amar. Are there more questions? So let us thank Aline again.